Hi guys, my name is YZ7IK4R, and today we're back with another video, another episode of Consultant Explains Maths. First of all, I'd like to explain why I was on a hiatus for almost a year. Well, work happened, and I wasn't really in the mood to make any more videos after that. But now I certainly have ideas that just sprung back to life. So here it is. Today I want to talk about two polynomial hacks, as you can see on the top left-hand side of the screen, that I was taught about when I was in senior high school. So during that part of my life, I was preparing for my university entrance examinations. They have those things in Indonesia, kind of like the JEE in India or the the Gaokao in China, but on a much less difficult level than those two. And it's basically like a collection of multiple choice questions in multiple different areas. Like there's like a psycho test like part. There's mathematics, Indonesian, English, and then like if you're attempting to major in something related to science or STEM degrees, then you will have another set of papers containing scientific maths, physics, chemistry, and biology. And in each of the in each of the math papers, you have a set of 15 questions that you have to solve together with the other subjects in a tight time limit. So that you're not actually expected to finish all the questions. You're only expected to score as high as possible compared to your competitors. Because of this, most people usually go into tutoring centers in order to prepare for those kinds of exams, which emphasizes speed over actual understanding of the materials, which has been a point of critique, but it's for another story. But here, I'm going to explain two of the hacks that I was taught about when I was preparing for those exams, and they will be about the roots for polynomial. Most often roots of a quadratic, because that's like the simplest polynomial there is, if you don't count linear polynomials. Anyways, so we have two hacks here, and we have to start off with ax squared plus bx plus c. This is a polynomial. This is a quadratic. Now we assume that this has roots x1 and x2. Now we have two hacks related to this form. Number one, if this holds, then the quadratic formed by swapping c and a around, or in other words, cx squared plus bx plus a, then has roots that are equal to the reciprocals of the original roots. So 1 over x1 and 1 over x2. And this, you need to assume that x1 and x2 are not 0. So neither of them may be 0. The second hack here is related to the sum and product of the roots. The sum of roots, which is denoted by x1 plus x2, is equal to negative b over a, while the product of roots is equal to x1 times x2 equal to c over a. So when I was in senior high school, I didn't really take much thought in any of these shortcuts, meaning that it looks as if it's just pure magic. But when I was in university, I realized that both of these are legitimate shortcuts and can actually be proven in a simple way. So here I am about to explain why these hacks work. Let's start off with the first one. Oh, by the way, I will also be talking about how they extend to other polynomials, not just of degree 2, like quadratic, but also of degree 3, in other words, a cubic, or even a general degree. So let's start off with the first one. So the first thing we have here is that we have a quadratic ax squared plus bx plus c with the roots x1, x2. Now, x1, x2 can be stated in terms of the actual root that you can get by using the so-called ABC formula or the quadratic formula. So x1 here is equal to minus b plus square root of b squared minus 4ac over 2a. The second root is almost identical to the first one, but with a negative sign instead of a plus in the middle. So it's minus b minus square root of b squared minus 4ac over 2a right here. So these are supposed to be the roots of the first polynomial. Now let's check the roots of a polynomial that we can obtain by swapping c and a. That means cx squared plus bx plus a here, it will have roots. If we call those roots x1 prime and x2 prime, then we get this. x1 prime here is negative b plus square root of b squared minus 4ac over 2c. And x2 prime is also equal to x1 prime, but with a negative sign in the middle. So we have to prove that any of these forms are equivalent to any of the other original forms. So what does that mean? We have to check what happens when we take the reciprocal of x1, for instance. 1 over x1 here is equal to flipping the numerator and denominator around. So you get 2a over minus b plus square root of b squared minus 4ac. We can simplify this by multiplying both the numerator and denominator by the conjugate of the denominator. We get 2a times minus b minus square root of b squared minus 4ac over, well, this one, quite long. We're going to leave the numerator as it is, but let's take a look at the denominator. The denominator is actually a factorization of a difference between two squares, which is like this. Now, we can see that the denominator can be operated here. The b squareds cancel out, leaving us with 4ac, and then we get 2a times all this. And then 2a and 4a can cancel out to give a factor of 2, which means that the final result here is minus b squared minus 4ac over 2c, which is actually x2 prime. Now, we don't actually have to label the one with the plus as x1 prime and one with the minus as x2 prime. So we can actually flip the numbering around. It doesn't really matter because there's still roots of the second equation, second polynomial here. So you just call this x2 and this one x1, which means that for simplicity, we can call that 1 over x1 is equal to x1 prime. And the same thing applies to x2. So we have proven that by flipping the coefficient of x squared and the constant around, we get a polynomial whose roots are just the reciprocal of the original what is it? Polynomial. Now, I was curious back then if this applies to higher degree polynomials. Let's try to extend this, all right? So for instance, if we have a cubic equation, that is ax to the power of 3 plus bx to the power of 2 plus cx plus d, and we assume that this has roots x1, x2, x3, neither of which are 0, then we can get a cubic equation whose roots are 1 over x1, 1 over x2, and 1 over x3, simply by reversing the order in which you write down the coefficients. So instead of a, you have d x to the power 3 plus cx to the power 2 plus bx plus a. And this has roots 1 over x1, 1 over x2, and 1 over x3. Like this. Am I wondering, is this magic? Well, no, because this actually can be easily shown for any polynomial of any degree. So in the general case, we'll be looking at a polynomial like this, an x to the power of n plus an minus 1 x to the power of n minus 1 plus dot plus a1 x to the power of 1, which I'm not going to write, plus a0. Assuming that this has roots x1, x2, dot, xn, and by the way, they can also be imaginary. The only thing that they can't be is 0. May be imaginary. Then the polynomial obtained by reversing the order in which we write down the coefficients has roots that are just reciprocals of the original polynomial. In other words, a0x to the power of n plus a1x to the power of n minus 1 plus dot plus an minus 1x plus an has roots 1 over x1, 1 over x2, dot 1 over xn. How do we show this? Well, it's actually quite simple. It's simple, but it can be a bit long just because you have to write down all these for precision. So a proof goes like this. Because each of x1, x2, and xn are the polynomial, are the roots of the first polynomial, we're going to call this first and second. Then, by definition, if you were to substitute x with x1 or x2 or any of the x something, then it will evaluate to 0. So we substitute x equals xi for more like for any I in the range 1, 2, 3, all the way to n. But choose one. Just choose just one, and then you'll see why. So here, an xi to the power of n plus an minus 1 xi to the power of n minus 1 plus dot plus a1 xi plus a0. This should evaluate to 0 because xi is a root of the first polynomial. Okay, so we're going to label this number 3, equation number 3. Now, our hypothesis is that each of these solves the second equation, the second polynomial, meaning if we were to substitute 1 over x1 into second polynomial, then it should be it should evaluate to 0. Let's check it out. So this is into 1, forgot. Substitute x equals 1 over xi into 2. So we have a0 over xi n power of n plus a1 over xi to the power of n minus 1 plus dot 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 plus a n minus 1 over xi plus a n. Now we don't know what this evaluates to yet, but we can just operate this by taking the least common multiplier, or sorry, least common multiple of the denominator. So we get xi to the power of n as the LCM, and the numerator becomes a0 plus a1 xi, because the denominator of a1 here is already xi to the power of n minus 1. So we're only left with 1 instead of xi, plus dot 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 plus a n minus 1 x I to the power of n minus 1 plus a n x I to the power of n. And you see this form is exactly the same as number 3, which means that this should evaluate to 0. And by definition, because we have found something that if we were to substitute x in the second polynomial with such that it divides to 0, then 1 over xi is shown to be a root of 2, sorry, of the second polynomial. And this holds for all I in 1, 2, and n. It's great. It's great that this trick also works for polynomials of degree 4, 5, 6, and so on, even though you might not be able to explicitly state the roots of those polynomials. Now let's take a look at the second hack. The second hack is also concerned about the roots of a polynomial, of a quadratic, but this time we have to add and multiply them together. So, as a reminder, let's rewrite the first and second roots of a quadratic. All right, so this is assuming that we have this standard quadratic. If we were to add x1, x2 together, we get this. So the expression inside the square root cancels out, leaving us with minus 2b over 2a. And that means we can cancel out 2 together to get negative b over a as a sum of roots. For the product of roots, we have x1 times x2, and that is equal to minus b plus all this. Hold on. Sorry, not 2a, it's 4a squared. Now the b squareds here vanish. cancel out, leaving us with 4ac over 4a squared. And 4 and 4 can be cancelled out. A and one of the a's here can also be cancelled out to give us c over a. So it looks like we have obtained these two results. The sum of the roots is equal to negative b over a, and the product of the roots is equal to c over a. Seems easy, right? But what if we have a cubic and we also want to see the sum and product of all roots? Well, it's a bit of an extra credit at that point, because you're not really supposed to think too much about the sum. Sorry, not even the sum or the product of the roots. You won't even be able to think about the roots of a cubic themselves, because the formula for that is quite complicated, and the formula for the roots of quartic or a fourth degree polynomial is even more convoluted. But you'll be surprised to find out that these kind of relations hold, or maybe not hold, but like there's a similar relationship. So for a cubic like this, then if it has roots x1, x2, x3, then the sum of all roots, starting with 3 terms, is equal to negative b over a, which looks to be the same as the one with the quadratic. But this time, the product of all roots is equal to negative d over a. Now notice that here we have a pattern, seemingly. Okay, we only have 2 sample points, but it looks like, well, we're drawn to patterns. So we have the first coefficient of the cubic, which is a, and then we have the second coefficient, b, and the last coefficient, which is b. Same goes with the first one here. What you might not know is that there is an intermediate result. Between the sum and product, there is an intermediate, which is the sum of product pairs, if you would like. So x1, x2 plus x2, x3 plus x1, x3, like this, which is equal to c over a. And you remember wondering, how could this arise? Well, this even holds for even larger polynomials in its generality. And this kind of thing is called the the Fieta formulas. The Fieta formulas, which was studied by Francois Fieta back in the, well, let's say a long time ago. Let's face it, a long time ago. So basically, this pattern, this hack is actually part of a larger pattern that continues for polynomials of even larger degrees. And it might be a bit convoluted to write down, but I'll just type it out for you, not type it, I just write it out for you to explain what it looks like. All right, this is the Fieta's formula. Okay, this might seem a bit intimidating, but let's just break it down. And basically, this left-hand side tells you, assuming that xi is a root, all right? So x with an index is a root. So the left-hand side here shows the way in which you want to combine the polynomial, the roots of the polynomial. So here we can find things like x1 plus x2 plus blah, 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 plus xn, which is like the sum of all sum of all roots. And then you will be able to find x1, x2 plus 1 x3 plus dot 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 plus xn minus 1 xn. But it's like, so this is a sum. This is the sum of all pairs, if you will. And then we can now take a look at the right hand side here. So the right hand side tells you what the left hand side is supposed to be. And here we notice that the sum of all roots is equal to, let's say, -1 to the power of 1 times an minus 1 over an. So negative of the second, the second, I was going to say second to first, which is redundant, second coefficient of the polynomial, while the an here is the leading or the first coefficient. Is it the coefficient of the largest degree? For the second one here, the sum of all pairs, we have -1 to the power of 2 times an minus 2 over an. So an minus 2 here is the third coefficient, or the coefficient of the third largest degree, the largest power of x in the polynomial, and so on and so forth. So this left-hand side here tells you if you vary k, so the first one is k, and k is equal to 1, so that means there's only product of one root, and then the second line here is when k is equal to 2, so that means you have a sum of product of two roots. If we keep going until k is equal to n, or the whole, what is it, the full degree of the polynomial, we get kn, which is equal to, we get k equals n, which is equal to, which is equivalent to saying the product of all of the roots here, which is going to be -1 to the power of n times a0 over an, which means the a0 here is a constant, and an is again the first, the leading coefficient, and -1 over n here depends on how depends on the degree. If it's an even number of degree, as in 2, 4, and 6, and so on, it's a positive, and it's an odd degree, and it's negative. Hence, why in the formula for the first, in the formula for the quadratic, the product of two roots here has a positive sign, at least here, while in the cubic, the product of the roots has a negative sign. It looks like this daunting task of trying to prove this relation is, well, out of our hands. But let me tell you, we can do it. Don't worry, it's only Francois Fiat formula. Nothing too special. Oh well. Anyways, how do you prove the above relation? Well, we have to go to basics here. So the proof of this is to notice that if a function, if a polynomial has n roots, then it has two ways of writing that a polynomial. One is, well, just writing out a polynomial with descending powers, like an x to the power of n plus an minus 1 x n power x to the power n minus 1 plus dot 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 plus a1 x plus a0. So this is the normal way of writing a polynomial, but we can also do better by putting a different way of writing a polynomial. That is, by writing out x minus x1, x minus x2, dot dot dot, x minus xn. Now, why is the right-hand side valid? The right-hand side is valid because this left-hand side has roots x1, x2, and xn. Because of that, it should factor out in a field of complex numbers as the right-hand side. Why am I saying complex numbers all of a sudden? Well, because it doesn't have to be real. It can also be complex. Things like, say, x squared plus 2x plus 4. This doesn't have real coefficients, right? It's not it doesn't have real roots. The roots of this is equal to -1 plus minus 4 minus 16 over 2, which is negative 2, sorry about that, equal to -1 plus minus square root of 3i. But you can say that this is x plus 1 minus square root of 3i and x plus 1 plus square root of 3i, like this. So it doesn't matter if the roots are complex. We can still factor them out in the realm of complex numbers. It doesn't really matter. So what is the next step here? Next step here is to try to multiply the right-hand side. As you are thinking, we don't even know n. Well, we don't need to, because we can just use patterns to describe what the right-hand side should look like. So notice that when you try to expand the right-hand side here, any term before like trying to simplifying them by collecting like terms and so on and whatever, is actually a product of either x or a root. So basically, let's just use an example. So in a simple factorization of some polynomial of third degree like this, you can probably guess what it's supposed to be. But if in case you couldn't, there should be 8 terms here before simplifying. One is multiplying all x's together. So that means choose x, x, and x. Don't take that out of context. Choose x from the first bracket, choose x from the second bracket, choose x from the third bracket to get you x to the power of 3. Okay. Now, for the second term, it can be anything. Let's say I want to instead choose -3 in the third bracket. So you choose x in the first one, choose x in the second one, and choose -3 in the third one. So you get -3 times x squared. So we have 2 combinations. So you can continue, and then you would have 8 terms in case, assuming you did not try to collect like terms and operate them. You get 6, sorry, -6 is your last, what is it, term. And you have other terms to fill in here, but each term is actually, sorry, can actually be obtained by choosing either x or the root. Hence, we have this expression for the right-hand side. All right, so you might be wondering, how could this materialize out of thin air? Well, this is actually just a direct result of the, what is it? It's actually a direct result of the description I gave you earlier about the right-hand side. So if we choose k, if we choose x k times, then we would choose the root, any root, n minus k times. And this is where -1 to the power of n minus k comes, and x to the power of k comes. But what about this middle term? This is a product of the root, but with the exponent b1, b2, bn. So each of bi here is actually either 0 or 1, and it's 0 if xi is not included. And then it's 1 if xi is included. And don't forget that these are just one, what is it? This is just one individual term. There's actually a sigma. We actually sum up all the possible sums here, going from k equals 1 to k equals n. Or is it really? Well, kind of like that. Okay. Basically, you have to exhaust all possibilities of the terms on the right-hand side here. So you have to write down all the terms. Okay. What happens after this is that you will have a set number of terms with k being equal to some number. What I mean by this is that you'll have you have a term that only has like that only has one root. So that means only one of how do I explain this? So basically, the terms will have a set number of the right hand side here will have a set number of terms with only one of the I is equal to 1, and then only 2 is equal to 1, only 3, and so on and so forth, until eventually you get to the term where all of b1 is equal to 1, all of bi is equal to 1. So there's actually like a double sigma if I'm not mistaken here. But basically, you have to exhaust all terms and then obtain like every single possible choice that you can make here. It's kind of like tossing a coin to the power of n times. So eventually, you will have a certain number of, a certain number of, oh, don't forget when none of them are 0, all right? So basically, this review Pascal's triangle to find out how many terms of this that is possible. But here you have the idea that eventually you'll have you will have an to the power of sorry, an minus 1 n minus n, which means that that means, all right, sorry for the long delay. Yeah, I was just thinking. I had to think quick. So the first thing you have to see here is when k is equal to n. That is when you want to find the coefficient of n, sorry, coefficient of x to the power of n, and that is going to be an minus negative 1 to the power of n minus n. All the x1, x2, and xn will have exponents to 0 because none of them are going to be active in a way. And then x to the power of n. Simple. And then for the second coefficient, we're concerned about the second largest power of x. So that means when k is equal to n minus 1. When k is equal to n minus 1, this is when k equals n. This is when k is equal to n minus 1. We have an times minus 1 to the power of n minus n plus 1. So that's n negative 1 to the power of 1. And now you should be grouping. You should be grouping x1 plus x2 plus x3 plus blah, 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 all the way to xn. Why? That means we are only letting one of these active, one of the roots active in the multiplication. And then at the end, we have x to the power of n minus 1. And then we keep doing this. This is just a very hand-wavy way of proving it, actually. All the way to the last one, where k is equal to 0. When k is equal to 0, we have an minus 1 to the power of n times all the roots being active, meaning that b1, b2, and all that is equal to 1. And in the end, x to the power of 0, which is equal to 1. So these should be equal. The green one, the purple one should be equal because the purple one is just the right-hand side being a bit more convoluted. Now, we divide both sides by an in order to equate both coefficients. Because the left-hand side and the right-hand side represent the same polynomial, then if it has the same, if two terms on the left and right has the same, degree of x, then they should be equal because those degrees of x don't appear anywhere else. That means xn plus an minus 1 over an x to the power of n minus 1 dot 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 plus a1 over an x plus a0 over an is equal to, now the right-hand side here has a coefficient an, has a term an in each one of these. So you get negative 1 to the power of n minus n, which is just 1. And then we get x to the power of n plus negative 1 to the power of 1, x1 plus x2 dot 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 plus xn, and so on and so forth until you get to the last term. Because this, we can equate the coefficients. So that means this is to this. This is not shown, but this is also to this. That means you get the theater formula, admittedly quite hand-wavy, but it's because the right-hand side has a pattern that we can exploit, which means we don't really need to write down the full form of the right-hand side. Hence, the theater formulas are proven. It's quite beautiful that what happens when we try to expand uh, all these theory beyond being able to just do questions on exam, which is a great thing by itself. But you realize that there are more types of polynomials and quadratics, which inspired me to just make this video and talk about what I found really. I know it's not new, it's not groundbreaking, it's been around for hundreds of years, but hey, it's my channel. So yeah, if you get anything out of this video, make sure you leave a comment, you like, and subscribe to this video. All right, so it's been YZ7IK4R, and see you in the next video. Bye.